LightSquared can complement GPS. Not only can coexist, it can complement it. The topics that I will talk about today are root of the technical problem for combining GPS and LightSquared. I will go into technical details of our solution, and I'll try to make it fast and also understandable for as many people as I can. And I will show 4 different ways of showing that what I proposed, it really worked. And then also talk about interference analysis feature and technology roadmap related to LightSquared. Every positioning, navigation, and timing device has one more element in it, and that is communication. You can hardly find any PNT device that doesn't have communication in it, and our GPS devices are as an example. On the left side of a typical receiver, you'll see our GNSS board that we have perfected it over many years. And on the right side, you see the different types of communication that we use in high precision applications that we still have problem with. This 6 modules, one is Wi-Fi. It's good, but it's not available in the field. GSM is good, GSM GPRS, it somewhat works. It is not really, is a little expensive, and it's not as reliable as we hope. LAN is very good, but it's not available in the field. The spread spectrum has a very short range of about a few hundred meters, maybe to a kilometer at most. L-band receivers, they somewhat work, but they are monopoly of Trimble and John Deere. We have the hardware, but we cannot use it because we don't receive authorization from them. But also, they have their own problems too. UHF, similarly, is not a universal thing. It needs certification in every country. It is not, again, reliable. It has a short range of maybe 40 kilometers. So in the PNT business, we don't have a good partner for communication. So, and when I heard about what LightSquared is going to do, that's what I put this chart up, that we love LightSquared. And we don't love LightSquared because, I mean, of course, we are one of the 260 million or whatever users that are going to benefit from LightSquared. But my focus is what they can do for GPS. Now, what is the technical problem? I'm going to go into this, explain the details, and say, how did we solve it? These are the cast of characters on this discussion. By the way, am I blocking your view from this side? It's okay? Okay, this cast of characters, on the left side you see 2 rabbit ears. That's LightSquared. I call them, there are 2 ears, 10L and 10H, which in this presentation I will focus on their 10L only. The right side also, there is similar thing, it's LightSquared 10R. On the bottom of the screen are the frequency ranges, the numbers in there. These 3 are those that we need to defend against. And who are we? We are deep in this basement, GPS and GLONASS. So, and then LightSquared in this side, we are in this side, and we need shield, we need fence. There are 3, these things in here, there are 3 kinds of fences that typically have been used so far in the market. This blue one, narrow in the middle, is for low precision receivers that have only 2 megahertz. They use 2 megahertz width of this signal, and those are typical Garmin and other receivers that used for navigation type things. Then this yellow shield is for high precision users, and then the purple one, the wider one, those that are more accurate, also those that cover 2 other partners down here that are Starfix and OmniStar, which I'll talk later. But let's focus on GPS and LightSquared and the shields around them. So you see the shields, they're not the real fence. They don't block us versus LightSquared nicely, because this, you see all 3 of them, it goes into LightSquared area. So this is the problem. Now that I want to talk about numbers, we engineers use, instead of 10,000, 100,000, and trillions, we use dB, and I want in 30 seconds, to those of you that don't know what dB is, I make it very simple. When we tell you 40 dB, we mean 10,000. So anytime I say 40 dB, or you see 40 dB, don't read it as 40. Read it as 4 zeros. If I say 60 dB, don't listen 60. Listen 6 zeros, and put 6 zeros in front of 1. So 60 dB is 1 million. 90 dB is 1 billion. And 12 dB is 120 dB is 1 trillion. If I said it wrong, I'll repeat again. 60 dB is 1 million. 90 dB is 1 billion, and so on. So I go using these jargons and these numbers to put everything in perspective. LightSquared, the tall thing that you saw, that was a representative of their power, we say it is 1/10 of milliwatt, but because we are not going to use milliwatt this anymore, we say minus 10 dB. So 10 dB was 10, minus 10 dB is 1/10. Minus 20 dB is minus 1/100th. And 20 dB was 100. So this, you see, LightSquared is minus 10 dBm, means 10 dB milliwatt. GPS, military, and CA code power is minus 133 dBm. Now you see why we are using this. Otherwise, I cannot read this number even for you. 1/20 trillionth, or something like this. And then GPS encrypted P-code power is minus 143 dBm. The reason I go specifically through these numbers with you, because I want you, every one of you, see numbers and see how close we are in our solution or how much headroom we have. So we start with this. Our LightSquared on the left is minus 110 dBm. GPS minus 143 military version, and then, minus 133 dBm military version, and minus 143 dBm, which is 1,000 times lower, or 10 dB lower, is the civilian version. I'm speaking very loosely the difference between military and things in terms of power. Their powers are the same, but because of the encrypting it and all things that we do, at the end it looks like we have this much less power. Okay, so now one thing about minus 10 dBm of LightSquared. First, I talked to LightSquared engineers and those that deploy all these towers and everything. They say typically they have minus 40 dBm, which is 1/10,000. It's very rare that you get minus 30 dBm. But I took minus 10 dBm. That is absolutely, positively, never in the world you may get such a power. So what we are testing with is absolute superpower that can never happen. Or now, the picture of the filters that you saw in here, which again I forgot to give the credit to the person that created this chart, and it's good that we all use the same chart that was created by.
That's all you've used so far.
Oh, okay. And, okay, so this is the filters that you see in here. It's like an artist rendition of the thing, but the actual thing that I measured in our receiver is like this. So we are really wide open. That is the root of the problem. There is no fence between us and nobody. It's not only, it's LightSquared, whoever else around us doing anything, we are invited into our receivers. If some of the surveyors you may see somewhere you go and it doesn't work because harmonics of some radio stations near you, we have no fence. And until there was no discussion about LightSquared, we didn't get serious to talk about our fence. Okay, so every test that I want to do, we do 4 types of tests, for the old ones and for the new one. One is component analysis and simulation test. It looks like you look at a person and say, this person looks healthy. He can talk, he can walk, and he's not crippled, he doesn't walk with crutches, everything. It looks healthy. So we go to the next step and we do sine wave in-circuit measurements. This is like EKG test, that we connect this machine to all the bodies of the person and we follow the behavior of all the organs and we say, okay, this person is healthy. Next is anechoic chamber test, which is what NTIA was doing, and we are doing a lot more than NTIA was doing. And this is like, it's a stress test on a treadmill and just do more tests to make this person is healthy. And one thing that I say, the ultimate test is look at the person. If he is a gymnast, you say, perform gymnastic and do all this double and triple, everything that we say, yes, he can perform the job. And in our GPS thing, it's like you say, we check all the multipath and all the behavior the very precise receiver needs to do. So these all 4 tests together are going to tell the thing is good or not. So for our old filter, this is the first simulation test. We look at it, it's wide open. Everything from here to here, there is no fence. So the person doesn't look good. But we go, and this is the group delay of that filter. Then we go still to the next one, and we show the sine wave in-circuit measurement on the old filter. This was our old filter that consisted of 2 ceramic filters, each $20. What we do in here, we inject GPS signal at minus 100 dBm, and then LightSquared signals at different frequencies, and we look at the output of our antenna. This is a close-up of the beginning. Everything is, things are injected in here, and then the output is saturated. So the second test also says this body is dead. Solution. This is what the filter was. This was the problem, and this is the solution. This is the filter that we designed. I go back. This is what it was, and this is what it is today. It's giving a solid defense and a solid fence, a solid wall, as thick as the wall of China, between us and the 2 sides of LightSquared, 10L and 10R, what I call it in here. All these slides that you see later, on the left, when you see 10L is this signal, and 10R is the one on the right. Now we look at our first test to see if it passes. This is our simulation and component analysis. Yes, it looks very good. The band here is LightSquared in this area and in this area, it's out. And the amount of putting LightSquared, blocking it goes to up to minus 90 dB and minus 80 dB. It looks good. I'm not going to make any final decision. So this looks good, and this is its group delay of this new filter that also, it doesn't matter much to us because group delay is not that important, as I'm going to show it to you. So we go to the second test. Sine wave in-circuit measurement, putting EKG probes inside and then follow the signals to see what happens to them. This is a picture, things of our test. We inject RF signals in here, and with this active probe, we measure. Let's see how does it work. And also, I want to say the signal that we inject at the frequency, we don't take the middle of LightSquared on the left. We take the extreme right to be the most conservative. We inject it at this point that is the closest to GPS. And on the right side, we take the extreme left, which is the closest to GPS. So with that, this is our new filter system. What we did, we replaced the two SAW filters, $20, thanks, two ceramic filters that were $20 each. We replaced, for the total of $40, we replaced with one ceramic filter of $30, followed by cascade of 4 SAW filters with LNAs that we had. And then in here, we saved about $10. So innovation also saves money. This did not increase our production cost. Now, the size of this SAW filters is like this. Here is a dime, and you see 6 SAW filters below it. It is not easy even to handle this. Okay, now we go. In this slide, we inject signals at these numbers, and we follow what will happen to the output of our LNA system. I will zoom in. This is the beginning, and we inject at these locations the signals that I mentioned. We put minus 100 dBm for GPS. Why I said GPS is minus 133 and minus 143 dBA. That's pure GPS. But we don't have pure GPS. It's buried in noise. And to be realistic, I put 100 dBm in here. That's what it usually goes into the system. And then we have minus 10 dBm of LightSquared. What it happens, and also, I just bring this to your attention. Every filter has a characteristic. It's called, I'm going to get a little technical, but bear with me, it's easy. Every filter has a characteristic that says how much of power it can tolerate without just getting saturated or without losing its perfect characteristics. At this frequency of 10L has plus 10 dBm called compression field. LightSquared is minus 10 dBm. We are at plus 10 dBm. The difference is 20 dBm, a difference of 100 times. We have headroom. we have margin even 100 times more than minus 10 dBm of LightSquared. And on their other frequency, we have plus 8 dBm of compression. It means at the signal that LightSquared is going to give us, we are going to operate perfectly. We are not going to get saturated. I continue to the middle and skip at the end. At the end, our output, GPS was minus 100 dBm. It became minus 67 dBm, 33 dBm of amplification. But LightSquared, which was minus 10 dBm, it became minus 68 dBm, and the other minus 70 dBm. So before this first stage, LightSquared was up and we were down. Now it's level. Within we are 1 dB above. GPS is 1 dB above in this frequency and 3 dBm above of the second LightSquared frequency. So this stage we passed, we go to the other stage, which is our RF system. I'm following the same path and looking at the same numbers as it goes through stages of LNA and splitter and attenuator and filter and another filter and mixer in the middle. So these numbers, I understand, I will zoom in and go through them. You see how the numbers change, but it's not easy to follow this, so I put them into this Excel sheet. This is how we started. Minus 100, minus 10, minus 10. At the output of a filter system, it changed minus 67, minus 68, minus 70. On the right side, I show the difference of GPS L1 minus GLONASS first signal, and the other is GPS minus GLONASS, minus LightSquared second frequency. So first column, I repeat again, is GPS minus 10L of LightSquared, and second is GPS minus 10R of LightSquared. As you saw before, when we started, we were minus 90 dB below. If you go through these stages, which you can see the numbers, at the end, we become 104 dB above LightSquared. And in the right side, 110 dB above LightSquared. If you read, what is 110 dB is 1 followed by 11 zeros, which means what? What is 11 zeros? Is 100 billion. We started like trillion times below LightSquared. We ended up 100 billion above LightSquared. It's gone. We don't see LightSquared. These are, again, look, this is our second test. We're just following the blood pressure or whatever through the system and say, it's healthy, we are healthy, we don't see you inside our system, LightSquared. So this was, I started giving GPS minus 100 dBm, which is GPS plus noise. Now, if you guys want to see how we are, just for the sake of fun, you want to compare how these signal differences were relative to pure GPS signal. Okay, I changed the first column. Starting from minus 100, I do minus 133. And our difference at the beginning becomes minus 123 dB. And then at the end, we are 71 dB above that too. Again, it just, for those that want to see, follow the numbers at how we are doing. This is if you want to compare.
Just where you are, just so you'll know.
Okay. Okay.
Don't worry.
Okay. So this is about relative, these numbers relative to CA code and to military. But we are 10 dB below military because we pour civilian, high-precision application people that we contribute $90 billion to the economy. We don't have our own code. We kind of hacked it, and that's what we are using today, and that's why we are 10 dB below what military is using themselves. So this is, it was relative to our encrypted P code, these numbers. Again, if you want to see, we were minus 133 dB below, 1 followed by 13 zeros, we were below, and at the end, we are 61 dB, which is slightly over 1 million times above. So numbers speak for themselves, and these are measured realistic numbers. Now we go to anechoic chamber test. This is the third test that we look at a little about the performance. This anechoic chamber test is this, similar to NTIA, but we do more. And this is, we put signal generators of LightSquared and GPS outside of the anechoic chamber, and inside we have our GPS receivers to measure all the performance of this of the receivers. Why do we put it in the anechoic chamber? Because we don't want any interference from outside, and everything we want to be controlled. This is a picture of our anechoic chamber. Inside, we have, on the right side, we have 3 antennas, and the center is a passive antenna to only measure the power of being transmitted. On the left and the right, we can put 3 or 4 GPS receiver antenna for the unit under test. This is another picture. On the left side of this anechoic chamber, we have LightSquared transmitter and the GPS simulator, signal transmitted. On the left side, we receive it. The distance between them is about 10 feet. It's more than enough. The near field is about 1 or 2 feet. If receivers or antenna more than 2 feet away from each other, they don't have any effect on each other. 10 feet of separation is enough. Now, and this is the test equipment of GNSS simulator, RF power meter, RF amplifier, RF generator, the second part of simulator, spectrum analyzer, and everything. So we ran this test, and we see the result. This is something unique that we have in our receivers, and we used in this test, that our receivers have a built-in signal analyzer and interference analyzer. There is nothing you can buy in the world, no signal analyzer can do as good as this, because outside signal generators, 30,000, 40,000 or whatever, they measure the things outside the body of the patient. It says what the environment is. But this one measures everything inside the chip where the things are important. Okay? So, and then in here we see the shape of the spectrum. Here is quiet, there is no interference. And also we can see not only the signal strength and how the system performs, analyzing the electronic signals inside the receiver. Also, we can measure the signal strength of satellites after processing. So all this, okay, so we will show our result, and this is the summary of items that our signal analyzer can provide. We can see the location of interfering frequency. We can see the power of interference. We can see some control voltage that gives us information, and signal to noise loss, and some statistical data. This is a very important picture. This says at the 10L power of minus 10 dBm, we had no signal loss at all. Remember that I said minus 10 dBm is not going to ever happen. You will not see that much of LightSquared power, but at that we see nothing. In the middle, there is an AGC gain that is inside our receiver, that when it sees something, it will adjust for it. It doesn't mean anything bad or anything is going to get degraded. Our internal things need to kick in to adjust for things. Here, it even didn't see it to adjust for anything. Zero, absolute zero. Our receiver didn't see it. When it went to -4 dBm, our receiver started to see there is something else, and it adjusted 0.6 dB, and at the end, there was absolutely no signal loss. We continue with -4 dBm, and then the signal loss at the end, we lose 1 dB. Remember, when we say loss of dB at different locations means different things. At the beginning of antenna, if I say 1 dB of noise figure, it's much higher than, much more important than here. In our antenna, we have 0.8 dB of signal loss, or I say noise figure. In here, we have 25 dB of headroom. Even if it went down by 1 dB, nothing. By 2 dB, nothing. By 6 dB, we can do our work. When this receiver works in a normal environment, because of multipath, this signal to noise will go up and down by several dBs. 5 dB, 4 dB, 3 dB, and user will see nothing. And what's the significance that we ended at plus 4.5 dBm? Because we could not generate in our laboratory, we could not generate any higher power of interference of LightSquared. We may later, we get and we just kick it higher to see where we can see this stop working. Okay, this was anechoic chamber test result for the 10L. For the 10H, we cranked it all the way to plus 4.5 dBm. Our AGC even didn't see it. So those who are worried about the handset effect on handset, LightSquared handset effect on GPS, there is nothing. Up to plus 4.5 dBm, even our AGC didn't see it. Okay, now I talked about the ultimate test, zero baseline result. And this is what? This is the final test that we say, are you the same gymnast that you were before? Can you do the somersault that you were doing before? Can you do GPSU multipath as you were doing before? Now, this is the ultimate test, and when I was talking to some of our good friends yesterday, it was kind of unanimous agreement that, yes, this is the best test. So what is it? On the left, I mean, we get the antenna on the roof, which has an old, very wide LNA in it. It comes down, and we split it into two similar receivers. One goes directly to the receiver, one on the right side goes through a 16 dB of attenuation, and then goes to a receiver. Then we measure the difference between two receivers, because the antenna is the same. If we measure the distance between this receiver, it should read 0. Or it's a comparison of the two receivers. Now, look, this part is the same. On the left side, we have a wire which is clean. On the right side, we have everything. Our attenuator is there, differences between the receivers, and everything will add up. Whatever we see, this is the worst case to see the performance of this receiver that is all this beautiful characteristic of the GPS signal. Is it preserved? Can it detect multipath and everything? So we put the antenna is on the top roof of this building. The distance between the antenna to the wall is about 3 meters, 10 feet, 9 feet. And the height above it is like 5 floors, 30, 40 meters, or 100 feet. So it gets a lot of well-designed multipath into the receiver, both from below and from the above the antenna. 10 minutes to go. Oh, okay. So now antenna came from this top of the building to this receiver. Here is the splitter. Here, GNSS receiver on the left, and this is LightSquared LNA, and then the final receiver. This is the final result. Top is for carrier phase that high precision receivers are interested. GPS L1, GPS L2, GLONASS L1, GLONASS L2 processed separately. And then bottom is for carrier phase. Look, GPS L1, and we have two types of measurements. We have a feature in our receiver to measure and compensate for group delays through the whole system, including the group delays of the filter. That thing's turned off, and here is turned on. You see, for the GPS L1, in both cases, the baseline measurement or the error is 0.2 millimeter, is less than the thickness of your business card. All the measurements, all the errors that you add together, it's less than the thickness of your business card. Who in the world, in our GPS field, needs better than 0.2 millimeter? The best that I've heard is 1 centimeter plus 1 ppm for first degree, for first order survey, or for earthquake monitoring, whatever that we do. 0.2 millimeter of bias or something is something that exists no matter what, because you have differences between receivers. So this is the best test. It says there is nothing. For GPS L2, the same thing, 0.1 millimeter. Note my units are here in centimeter. For GLONASS L1, GLONASS does have interchannel bias problem because they are FDMA, they transmit in different frequencies, and that is why when we kick in our compensator or measuring group delays, we get improvement, and they are 0.1 for 1.4 millimeter. And for non-carrier phase people who are interested in the code, we get for GPS 4 centimeter, 5 centimeter. For GLONASS, again because of their FDMA problem, without calibration, we get 60, and with calibration, we get 7. Okay, this was the 4 different tests. The baby is healthy. It can do everything that you wanted, and it has absolutely no effect, even when we put the power of minus 10 dBm. That will never happen. We had still about 10 dBm of headroom above. So if LightSquared increases their power, we have no problem. I mean, increases from 10 dBm, minus 10 dBm. Now there is another quick things that I want to talk. There was a question about the aggregate effect of 44,000 transmitters on LEO satellites. The bottom line is that 44,000, even if everything lined up to hurt that one particular satellite in the air, all 44,000 aim their side loads toward that, they will end up with minus 58.5 dBm. Remember that our test was at minus 10. This is 40 dB. It's 10,000 times less than what we were testing. Now, measuring for group delay, I told you this is a technology that we had several year and a half ago that we measure for group delays. We introduced this for GLONASS calibration because they have different, they transmit in different frequencies. We were calibrating their interchannel biases to the accuracy of 0.2 millimeter, and we said our GLONASS is as good as GPS. And again, it's from slide from our 2-ion Institute of Navigation conference before that we calibrate up to 0.2 millimeter. And this is how we do. We just, inside our chip, we take code for GPS or for GLONASS with 15 megahertz carrier on it. 5 minutes, okay. Then we shift it up to the GLONASS or GPS frequency with a variable attenuator, and this way we measure. Like we transmit inside our receiver, we create a satellite, send it up to our antenna and bring it down, and this is how we are doing. And we measure group delay and things for our old antenna, for new antenna, for GLONASS, because for GPS, they are all in the fixed location. What is important for GPS? Remember those that are interested in timing applications, because the temperature changes. Due to the temperature change, the group delay changes from here we show from minus 40 degrees down here to plus 80 degrees, and we have this much change. For those interested, we will calibrate the group delay and carrier delay variations. And by combining these two, we can very inexpensively and dynamically, we can calibrate to the accuracies of few picoseconds. So this was for carrier delay. Previous one was for code delay as a function of temperature. Now, our technology roadmap, we said that in November of 2001, we will introduce a system that to protect us against LightSquared, and we did. On March, we are going to introduce this antenna, timing applications, making this group delay dynamic measurements available. And then on June 2012, my ultimate goal, and that's why I'm so interested about LightSquared, is to integrate their communication system inside our receiver, and we provide very fast, very accurate, very reliable RTK trouble-free anywhere in the nation. You go from one place to the other, you don't need to worry about your UHF frequency and other things. And this is our systems are available, is in production, and this slide that you see is out of our production facility, and it's something that when the antenna is built, they test it, and this goes as a certification with each antenna. I'm showing this to show you that we are in production, and this is our manufacturing facility in San Jose, California, proudly manufactures all of these things. And I understand, this is my last slide. I understand you say, I tested this, and this is honestly everything that I saw, I presented to you. You want to test, you want to conduct your own test, we have 40 of these units in here. It's available for whoever wants to test it today, and I like as a reminder of this session that we are here, somebody take some pictures, that these were my theoretical discussions, and these are things out of the production line. This is not engineering thing, this is not a sales pitch, this is what I want to show the status of technology, that this is theory and this is what it is. And thank you so much for your attention.